Hi, I'm Ben-Yaakov. This presentation is entitled DC Regulation of PWM Converters. Here is the problem that we are addressing in this video. I'm showing here a closed-loop power supply, the DC-DC converter, in which we have the power stage, we have the modulator which is producing the pulses for the power stage, the duty cycle you might say. Then we have the output coming out of the power stage with the load and a filter capacitor, and then we might have a divider that goes into a compensator in which we have the input of the reference, and these are compared and the duty cycle is produced such that the output will follow in fact the reference within the divider. The issue that we are addressing here is what happens if the input has a step or the output has a step, like the step of the current at the output, or a step in the input voltage. Well, we understand that when we have a step, we are going to have some disturbance here at the output, but the question that we are here concerned with is what happens later. Is it going to return to the same value as before the disturbance, or is there going to be a shift between the output before and after the disturbance due to this step? So this is called a regulation or DC regulation. This will be with respect to the input in the case of the input disturbance, or with respect to the output if it is an output disturbance. So the question is, how can we estimate and how much can we expect to be this different? Now this is important because in some cases we do rely that the output will be fairly constant. In fact, sometimes we are using it as a reference. So stability, DC stability of a regulator is an important issue. Now a regulator is operating in a closed loop, so this is in fact a closed loop feedback system, which this is the generic representation of this regulator. We have the reference, this is the summing junction, comparing the reference to the output or part of the output through a divider. And this error now goes into the compensator, phase compensator. This is needed, first of all, to get the gain which we need, and also to make sure that the system will be stable with the bandwidth that we want. And then we have the modulator, which is producing the pulses, and of course the power stage to the output. Now the difference between the feedback coming here, the output, and the reference is this error signal. This is in fact the error of what we want and what we get. Okay, we want this and we get this, and the error between them is this value. Now this value is therefore the difference between these two, and this V sub F is this V sub E times the loop gain. This is the loop gain. So I can plug it in here, and I'm getting the very well-known relationship that the error is equal to the input divided by 1 plus the loop gain. And now we're talking about DC, we're interested in DC, so I'm interested in the loop gain in the DC or very, very low frequency. Now usually the loop gain at that region is very large, certainly larger than 1, so it'll be like V reference over the loop gain at the DC. So now what about the disturbances? Now we can model the disturbances as extra inputs to the output, which are going through some transfer function, okay? So when we have a disturbance here, it eventually enters the output, but it is also affected by the feedback. Same thing for here. So now, how is this disturbance actually affecting the output? Okay, now this is again a feedback system. There is a transfer function between here and here, but this disturbance is now affected by the feedback, very similar to what we've seen before. So therefore, the error that we are going to get, that is the change in the output as a function of this delta I, will be this transfer function times delta I divided again by 1 plus the loop gain, and again the loop gain is much larger than 1. So this will be the effect of the output change in current on the output voltage. So now the question is, what is this transfer function? Well, we can find it out by opening the loop here. We can do it since we have just schematics here, there's no problem opening the loop. We'll open the loop and see what is the transfer function in open loop between delta I and delta V. Now, we have a delta I, now it's coming into here, in fact, and what it sees at a given operating point without feedback is this, if this is a buck converter, a buck running at a certain duty cycle, at a certain operating point, a certain V in, and as we look into here, we see a resistance. We see this resistance plus the resistance of the transistors, well, actually in parallel with R out. We're talking about DC here, so the capacitor is open circuit. And usually R out will be much, much larger. So therefore, the transfer function here between delta I and delta V in open loop is nothing but the resistances that we see here. So it is like the resistance of the inductor plus the resistance of the RDS on, both of which are very small, of course. Now, what about the disturbance at the input? Again, we have an input. We are operating at a given operating point. There is no feedback, certain duty cycle, and then we have a change in V in, which is translated into a change in this midpoint, and then this change is translated to the output voltage. So actually we have here a divider, okay? And this divider, of course, again, since RL is very small, is almost 1. So in general, we can say, with a very good approximation, that the midpoint is the duty cycle times V in, which is equal to V out, and therefore the change in V out is the change in V in times the duty cycle, and therefore this transfer function is in fact the duty cycle. So we have now the two transfer functions for the two disturbances, and the question now is, what is the loop gain? Now in a practical circuit, we're going to have an error amplifier, and then we have some network around it, which could be type 1, which doesn't have a very good performance, so let's leave it alone. And then we have type 2 and 3, and the difference is primarily this branch here. For the type 2, we're going to have such a network here, and for the type 3, there is an additional phase advance network here. But the point is that we are interested in DC, so this capacitor and this capacitor are actually open circuit. So in fact, this is what we have. We have an open circuit here, operational amplifier, open loop, and then we have this feedback system. Now in some cases, the amplifier is actually GM, that is a transconductance amplifier, but again, usually we are going to have this compensator here, the network, so therefore again, it's operating in open loop. So in any case, we are working in open loop, an amplifier with very high gain, operational or GM with very high gain, a DC open loop. And the gain could be something in the area of, let's say, 10 to the third, 10 to the sixth, something like that, depending on the amplifier. And therefore, you'd expect the disturbances at the output due to the output and input steps to be rather low, because we have this expression in which we are dividing this transfer function by the loop gain, which is very low. Next, I'm going to do some simulation to demonstrate this whole issue of DC regulation. I have here an average model of a buck converter. Here is the buck section here, inductor, capacitor, and load. And it is driven by a behavioral source, which is the input voltage, that is the DC, times the duty cycle. So this is the average voltage that you'll see, say, the midpoint, except that here we're talking about average. There's no pulsating here. It's only the DC component. And then we have the error amplifier, which has a feedback which is similar to type 2 compensator. However, I didn't do any effort to have a high bandwidth or good performance for transient, because we are only interested in the DC region. It has a large resistance here, which I'm going later on to change in order to reduce the loop gain. Now it is 1 gigahertz, and then we have here 100K, so the gain here is fairly high. And then we have the reference, which is 1 volt. We have a divider of 1 to 5, so the output should be 5 volt. This is the DC of the stage. This is just the power supply of the amplifier. And here I've added a step to the input as well as a step to the output. This is 1 amp, and then this is 1 volt step here, okay? And they are coming in sequence. Now the nice thing about the average behavioral presentation is of course the fact that you can run AC analysis, and by that you can get transfer function border plots both for the sections as well as the loop gain. For the loop gain, I've put here a source. This is an AC source. So as we know, in this case, the loop gain will be the ratio between the voltage here and the voltage here. So I can invoke it in AC analysis, while then I can also run, of course, transient to get the response for step at the output and step at the input. First thing to do if you are going to do AC analysis, to make sure that your operating point is correct. Otherwise, the AC analysis will be corrupted and you'll get some garbage. So I'm running an operating point check, and I see here that the input is 15 volt, which is okay. The output is 5 volt, and therefore the duty cycle is 0.3. 0.33 times 15 gives me the 5 volts, so everything seems okay. I'm operating at the correct operating point. And here is the loop gain. As I have said, there's no attempt to have a wide bandwidth. In fact, the crossover here is at, what is it, like 1 hertz. It's okay. We are interested in this region here. Crossover is at 90 degrees, so it's a fairly stable system in terms of stability, oscillation, phase margin. However, it's a slow system because the bandwidth is only 1 hertz, but we don't care about this in this particular presentation. And here I have the step response to a step at the input, 1 volt. This is this blue one. And then at the output of 1 amp, this is the red one. You see here the output. This is the response of the output. We have heavy transient. And of course, the time it takes is long because the bandwidth is very narrow. But again, we don't worry about this in this particular case. And what we see here is that after the transition, that is after the step, the DC value comes exactly to be the same. This is both for the V-in disturbance and also for the delta I disturbance at the output, okay? In both cases, it's coming back to the same thing, and in fact, we are within microvolt differences between before and after. So it works very good. We see that the high loop gain is really doing the job, and we are in good shape. What I didn't mention earlier is that I've put here a 100 milliohm resistance to represent the total resistance. So practically, the resistance seen from the input is the 1 ohm in parallel to this 0.1 ohm. Now I'm going to run a simulation with a much smaller loop gain. This I'm doing by replacing this 1 gigaohm with 1 megaohm. This is 100, so the gain from here to here is 10, because this is 0.1 megohm and this is 1 megohm, and this is like an inverting amplifier. So it's a very low gain, and we can see it here reflected in the loop gain, which also takes into account the other transfer functions, of course. And we see that the loop gain here is 14 dB, which translates into a factor of 5. So we have a gain of 5, a loop gain of 5 for this system, very low. And now we are exposing it to this transition at the input and at the output, the two steps. And of course, we see now a step at the output, both due to the step in the V-in. Here it is, this is this V-in, which is like 47 millivolts, that's a lot. And here's the measurement for the change at the output due to the current step, and it is 14 millivolts. This is quite a bit. Now let's do some sanity check. We have all the information we need, and let's see if the theoretical expectation is really matching these results of the simulation. So we know that the expected output change as a function of a step in the output current is the output resistance times delta I, which is 1 amp in this case. And here I'm adding again 1 plus loop gain, because the loop gain is very small, it's 5, so you cannot ignore the 1. Now the loop gain here is 5. The resistance that we see here is 90 millivolt, because it's 1 ohm in parallel to 0.1 ohm, 100 milliohm. And therefore, if you plug in the numbers into here, we get the expected change to be 15 millivolt, while we measure 14.16. I would say it's very good, excellent. So we see that we can say that we really understand what is going on, what are the reasons for the DC level changes at the output. Now what about commercial unit? So I'm showing here, actually it's a jig as they call it, of a controller by Analog Devices, LTC3703. This is actually the circuit suggested by the manufacturer, except that I've added few things. First of all, this is 1 milliohm inside this inductor. I've added a step current at the output, a step voltage at the input. This is the power input. And then here I've also put a large resistor, 100 giga, not to disturb the original design, so we can run it as it is, and then we'll do some experiments while changing, say, the resistance and the gain. Now in this case, this circuit is not compatible with AC analysis, so I cannot run AC analysis. There is a way to get the loop gain, actually in LT-Spice. This is the LT-Spice presentation, which is kind of cumbersome. I'm not doing it. I'm just looking at the time domain responses. So here it is. Again, we have a 1 volt step at the input voltage. We have 1 amp step at the load. And here's the output. We see that the change is really very small, while it's probably less than 1 millivolt. And again, for the current, it's probably even smaller. It's almost exactly the same. So again, probably the large loop gain is really attenuating, although there is some change here. And for the current, it looks pretty good. Now I'm going to change the resistance to 200 milliohm, okay, just to see the effect of it. And indeed, I can see here that as far as the load regulation goes, there is some deterioration, and this is because now we have 200 milliohm. Still, the loop gain is very high, but we can already see some changes. It's probably about eyeballing in something in a range of 1 millivolt or 2 millivolt. Again, it's very small because the loop gain is very high. Now I'm going to change the loop gain, okay? And this is done by putting here a 300 kilo ohm resistance, which is sort of bypassing the whole thing. So at DC, the capacitor is the open circuit, as well as this one, and as well as this one. So this is, by the way, type 3 compensator, but the capacitor at DC are open circuit. So basically we have this divider plus 300 kilo ohm. Okay, so this is the gain, fairly low. And I'm keeping here the resistance to be 200 milliohm. Now I see the following. First of all, I see a larger change due to a step at the output current. It seems like something like 2 millivolt. However, if we look at the input, the change is really small. Now, first of all, there is something interesting in that it is here negative. It's very small, but it is negative. That is, you increase the input and you get an output which is negative. Secondly, as we have seen before, the step is small, really small. It's not affected that much by the loop gain of the system. And the reason is that this particular controller has a correction for the input voltage regulation. That is, it has a feed-forward path. Now, the feed-forward is done in this way, in that there is a sensing of the input, and then there is a divider here between the output of the aero amplifier and the modulator. So, as you have a step here at the input, this responds immediately without having to go through the loop, through the aero amplifier and everything there. but it is responding immediately, like a feedforward, that's the name for it, by dividing this signal by V in, so therefore correcting for the change. So if the change is, say, positive, then this will actually reduce the output so as to correct for this change, and the controller from this point on will not see actually any change. So this helps not only for the DC regulation, it also helps for the transient response to a change at the input. To test this concept, I've done the following. Here is the same circuit again, but now I did the following. I've split the input into two parts. One is going directly to the controller, so the controller sees a constant voltage. So now it doesn't have this signal for correction because it sees a constant voltage. On the other hand, the half bridge here, the synchronous part, has this step here. So now the controller cannot correct for a change in the input because it doesn't see it at all. And this is again the 300 kilo ohm with the lower loop gain. Notice that there is an overcompensation, and that is that in fact the output voltage goes down a little bit. Without the compensation, without the feedforward, the voltage goes up as expected. That is, if the input goes up, the output should also go up. It's not very much, but we have an order of 8 millivolt change due a step of 1 volt at the input, but this is with a reduced loop gain. Okay, with the original loop gain, of course, we are not going to have this large DC offset, but we are going to have this transient. You see, this is a very nasty transient, while we don't see it here at all because of the feedforward. So what are the conclusions here? Now, first of all, we see clearly that the high loop gain improves DC regulation. There's no question about that. And that feedforward can help improve input DC voltage regulation as well as attenuate output voltage disturbance due to the input voltage step. So feedforward is really good when implemented within a controller, but if you try to do it yourself, it's not a simple job to do. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest and perhaps it will be useful to you in the future. Thank you very much.